see this from there. So can you read from there? I can actually.
Clone the same repo as before. It's the same repo, right? The example.
Same repo.
Yes, it is. Welcome back, everyone. My name is Golnoosh. I'm a postdoc at Link's group. And this is a hands-on, so I'm not sure if you already cloned this Git repository. So because we are going to try different models, I encourage you to actually clone it now. So if you have your laptop with you, you can clone it. So if you clone it, this is what you can see. So in this part of the tutorial, I'm going to do the modeling for these two directories, this user modeling and trust prediction. So it has two parts. The first part would be collective classification. That's, I have a running example, which is a user modeling. And for the second part, which is the link prediction, we are going to try some trust prediction modelings. So for the first part, it's a user modeling. I want you to go to this directory, which is a user modeling directory. Okay. Okay. So what is collective classification? Eriq already did go through an example of collective classification, which was predicting weather. And here I'm going to show you a template for, okay, can you hear me now? Okay. For collective classification task. So it could be anything, but I have this running example, which is a user modeling. So collective classification is that we have the graph, and we want to predict the label of the nodes. So the label of the node could be a weather of the city, Or it could be, for example, some label for the user. It could be, for example, age of the user, gender of the user, or personality of the user, which is the running example for this session. So we can define the predicate is, so the label of the node is this attribute. So here we're assuming that some nodes, which are user here, we know their labels, and we want to infer the label of the other nodes in the graph. So we are assuming that we have a training example, that's the set of users that we know their labels, and we want to infer the label of the target users. But it's not always the case for collective classification, so we could have a graph that we don't know the label of any of the nodes. So example of this predicate is, for example, the label for the gender of Alice is female, or age of Bob is young. And it's a nice way of modeling this because you can also have different categories. So for example, for gender, we have female and male. For age, you could have different categories like young, middle-aged, old, so you can have categorical labels. And for example, also personality, you can have different personality traits, introvert, extrovert, agreeable, openness, etc. So as you already seen, in collective classification, one of the sources we can use is local predictors. So for example, for the better one was the sensors of the city. And for example, for this user modeling one, if you are considering the social media, for instance, we have different content that users are generating in social media. It could be text, it could be image, that uploading their picture there, or they are, for example, tweeting. So we can use all this information associated to the user in order to do the prediction. So we can define a rule such as this. So prediction from the source is giving us a label for that node. Is it clear? Yes, okay, nice. So for the prediction, as you already seen, we need some training data. So for example, if you are using text of the user, we have to extract some features from the text and then train a classifier like logistic regression in order to do the prediction. So here I have drawn an example for the personality prediction. So I want to know whether a user is introvert or extrovert. And there are already papers about this that you can actually predict the personality of people based on their text that they are like publishing on social media platform. Here you can see, I'm not really going to read this, but it's a word cloud of the status updates of the Facebook users. And here is for the extrovert, and here is for introvert. So from the words you can see, like for example, extrovert users are like partying, while like most likely use the word party. And the introvert users are mostly use computer, internet, anime. So yeah. And this word cloud is coming from this paper. So one of the sources, as I said, that we can use is local predictor. So we can actually use the models that's already there for predicting the personality of people from their text. Another source of information, which is actually the main reason that we can use PSL, is collective rules. It's the relations between users. So for the weather example, the relation was just the nearest cities. So distance between the cities, we consider it as a relation between two nodes. But we have three types of relations that we can actually use. It's a relation between the nodes, for example, user-user relations, or like a city-to-city relation. We could also have another type of nodes like items, and we can also have this relation between these two types of nodes. Like for example, user-item relationship. If you are familiar with recommender system, it's type of relation that you'll get there. So like users are liking a movie, or for example in Facebook they're liking a page. And this type of relation is not between two users, it's between users and item. You can also use another type of relation, which is a group. So users are joining different groups, or you can actually run clustering. So you can have a cluster of users and you can use these kind of relations between users. And I have examples to show how you can actually do this in PSL. So for the first type of collective rules, it's a user-user relation, as I said. So for example, it's a friendship links or follower-follower links. It could be also a neighbor or like a singular user, so we can define some functions to define like similarity or distance between the nodes. It could be also some other relations, like someone is the spouse of another person, it's an idol for a user. It could be co-author, they were colleagues, so all the relations between users you can consider as the user-user relations. The thing is that in many of the machine learning techniques, they actually convert this kind of relations into a table. So I'm assuming that your question was about this, like you can actually convert this relation to a table, like for example here, if you have this user, this sort of relation between user, this edge list, we can actually convert it in this way that, for example, user is connected to whom with a one-hot embedding representation. But it's not a good idea, and I will let you know why. So we should actually use the actual graph, because by using this table representation, we are actually losing some information. So it's a collective rule for this, for example, user-user relation is a friendship link. So if two users are friends, and we want to infer the label of one of these nodes, we can use the label of the other node to infer it, right? So here, you can see that we have this, which is our target, as I said, that in this collective classification predicate is our target. We have it in both parts of the rule, the body of the rule and the head of the rule. And both of them is open predicate because it's our target. And this is important, and it makes it collective because you can jointly infer the value of this predicate. What does it mean? As like the example for the weather that we've seen, that for example we know the weather of San Jose and want to predict the weather of Santa Cruz, so we can infer it directly. But if you don't know the weather of San Jose as well, we can actually infer it collectively from other cities that we have in the data set. So we could have a scenario that we have this friendship link between two users, but we don't know the label of both users. But here, because we are doing it collectively, we actually can infer it. But if you are using the table representation, you're actually missing this type of information. So here's an example. So if, for example, Alice and Carol are friends with each other, and we know that Carol is extrovert, then we can infer that Alice is also extrovert. Another type is, as I said, could be two types of nodes. It's the, for example, user-item relationships that we can have in social media platform, like a Facebook page likes, for instance, or item ratings in, like in Amazon if you're just liking an item or like buying an item. It's also very well known that people actually represent it as a matrix. So the matrix factorization representation is one of the ways that people actually convert this user-item relationship to this table of user and item and one-hot representation. But as I said, we want to actually use the actual graph here and to use the collective power of this relationship. So here is, for example, if two users liking the same item, and one of the users we know the label, we can infer that the other user is most likely having the same label. So here is an example for personality prediction. So if Alice and Carol both like partying, and they like, for example, a page in Facebook about partying or partying events, and we can infer that because Carol is extrovert and Carol is also like the same item, Alice is also an extrovert user. The other type of relations is groups or clusters. So it's very similar to items, but you can use different techniques for clustering users, or you can actually use this kind of relation that you have it in your data as a way of defining these kind of models. So for example, if two users are joining the same group, we assume that they should have the same labels. So here, for example, Carol and Alice both join a group about the action movies, and we know that Carol is extrovert, so Alice could be an extrovert user as well. So now it's hands-on. So for the model that I described, I generate synthetic data. Unfortunately, I wanted to give Facebook data, but I couldn't do it because of this privacy issues. So I generated synthetic data to try it today. I'll ask you to go to this GitHub and then to this user modeling directory, the CLI. We want to try all of the models that we already seen. So the local predictor model, which is a prediction from the text and image of the user, the friendship links, the likes and joins, and then we will see what would happen if we all combine these models. So I want to ask whether you already cloned this Git repository. Yes? Okay. So I want all of you to go to this CLI directory. Okay. So what you can see here, you see a model, which is a user modeling.psl model. We also have this data, which is user modeling.data. So if you open the user modeling.psl, which is a PSL model, okay.
Check out the UAI2018 branch.
Yes. Good. So you have to actually check out the UAI2018 branch. Okay. So now, okay. So go open this. Okay. So you will see this model. Can you see the model? Yes? Okay. So this is a full model, but we want to try different parts of this model now, so separately. So let's clean. So first I will explain the model. So the first two rules are local predictor. So I said that if the user has this source, so for example the user is just have any text, and we have a prediction from a text for that user, and this is for the personality prediction. So we want to predict the user is extrovert or introvert. So if you have the prediction from that source, we can say that the user is extrovert or introvert. We have the negation of it as well. So if the prediction is saying that the user is, for example, introvert, we want to say that user is not extrovert. Okay. So this is the local predictor rules. We have the collective rules. We have the collective rules, which is the joining groups, and the likes, and the friendship links. Okay, is it clear to everyone? Okay. And we also have this rule, which is a bit different. And this rule is actually saying that for the labels that we have for a user, all the attributes, user should only belong to one of the categories. So if you have it, for example, for age, user should only be, for example, young, middle-aged, or old. Or for the gender, user should be either female or male. We could not have both. Okay, so let's go back here. Okay. So you already seen the model. If you open the data file, you will see something like this. So we have the predicates which are observed, which is the predictions. It has 4 arguments. We have friendship links, likes, joins, has it's a source, that the user has a source or not. And then we have this is, which is open, which is our targets. Okay. And we have all the observations that you can actually check it in this data files. And then the target is and the true value. So we have a true value for the evaluation purpose. Okay, so we can have it. And then let's try the model. So the first model I want to try is just using the local predictor. So what I want to ask you is going back here and comment out this. The other rules. So except the first 2 rules, we want to comment out all the relational rules. Okay. Then we want to save this model. I want to run it. So to run, you only need to do this. Okay. So let's run this model. So this model is only using the local predictor. Here we have 2 sources, which is image and a text of a user. So it's both sources that we are combining here. So what we're getting here is AUC 0.87. It's a really good number. What?
817.
Yes, 817, yes. Okay, so this is the first model that we tried. So let's go and see the second model. We want to try the friendship links to see whether these friendship links are actually helping us to predict the personality of people. So have you already get the results for the first model? Yes? Okay, nice. So let's try the second model. So what we are going to do is we are going to comment the first two rules and uncomment the friendship ones. Okay. And let's try the model again. Run the model. So what you can see here is the AUC is 0.50 something, so it's lower. And it's kind of understandable because it's not always that you are going to be friendly to someone which has the same personality as you. You are not going to be friendly with extrovert people all the time. So you have like extrovert and introverts among your friends. Okay, so let's try the third model, which is just using the likes, like the item that you are liking. So we are doing the same thing. So we are changing this model again. We are commenting the friendship links. And uncommenting these two rules. Okay. So now let's try the model again. The relational model takes more time to finish. What I want to show you now also is the data files. So while the model is running, what I can do is I can actually show you. Okay, we have the results, so it's about 0.7. But what I want to show you as well is the data files for the user modeling. So this is the data files, and if you look at actually the likes, it's observed one. So you can see that we have a user, and it's a tab separated that you already seen. And we know that the person is like anime movies or action movies. This is for the likes, and then for the joins that we are going to try now is we know that the user is like partying or like video games. Okay. Okay. So let's try the last model as well. So it's very similar. So what we are doing is just using these two rules and then comment out the other ones, and we can run it. So if you do this, you will get this result. So if we want to do random assignments, it's 0.5. If we do the local predictor from text and image, we will get the result 0.8. For the friendship links, 0.5. Likes, 0.7. And if you try to join, you will get 0.86. Okay. So what about like using all these rules together? So let's try that. Let's try all these rules together. So you uncomment all the rules. And then run the model again. So does anyone have the results already for all the rules? So the thing is, if you run the whole thing, you will get the result about 0.77. So I want to ask you to do something. So if you look at the model, the base of all rules is equal to 1. I want to ask you to use your intuition about the result that you are seeing and then change the base of the rules to see whether you can actually beat this. You can actually make the better model. So I will give you like a few minutes to try this and then see if you can get better results. have any problem running the model, just let me know and I can come and fix it. One hint is that we can actually use these numbers to see like which rules that we just try separately works better than the other ones, and then you can change the weights of the rules accordingly. That's kind of the dominant knowledge that as an expert, when you're doing the modeling, you can actually use to assign weights to the model.
So you're saying that if we're having, like, some rules might actually ruin, like, it's kind of interesting, like if you had, let's say, a decision tree, and you had some features that they were, noisy. In that case, the decision tree would be able to eliminate them.
Mm-hmm.
Maybe not logistic regression, it depends. So here we have to run the weight learning in order to.
Yes, but now I'm not asking to run automatic weight learning. I'm just asking you to assign the weights to the rules. This is something you can actually try for your own model. You can try the rules that is kind of like different source of information. Consider that if each one of them have different weights, and you want to know which one is actually a good predictor, and then try.
So what if you use a simple rule and weight the rules according to the AUC, or square them? Like, sometimes people do that as a heuristic. You run them independently, and then obviously the random one, okay, the local predictor, you put the AUC values. That would be interesting to see what it's going to, like, weight them according to the AUC that they give you.
Exactly. So it's nice to actually use the AUC, but not the actual value of AUC, because it's a
Something
relative.
squared, yeah.
Exactly. So you can actually try some heuristic, but it's not like that direct because it's collective. So you are trying all these rules together in order to get the results. So it's not like these two rules is like used independently from the others. But that's a good heuristic, so that's why I'm asking you to try. So is there anyone getting your results better than 0.77 using all the rules?
0.91.
Yes, and can you tell me the
10 for the joins and 5 for the local.
for the local predictor you use 5, and for the joins you use 10, and the others all 1. Okay, nice. So you get 91. Nice. Anyone else? You can actually remove the rule if you don't like to have it. So any sort of combination you can try. So what I want to show you now is one of the ways that you can actually try this. Let me show you this. So here, I assign weights to the rules. So for the first two rules, I assign the weights to 50. For the friendship, you've seen that it's not a good result, so I put it as 1. The likes was good, so 0.7, so 10. Joy was really good, so you say 0.86, so I assign 100. So if you run this model, and you can actually find this model in the directory's alternative models. If you run the model, so you copy paste it to the folder, you can actually run this model. And what you're getting is 0.91, so very similar to what you got. So you can actually play with the base of the rules and see whether you can do any better. So for the fusion, and this is data fusion, what does data fusion mean is that we have different sources of information and we want to combine them. PSL is very nice for doing it because you can have different rules representing each sensor and then you can combine it together. But as you see here, if you just combine it without knowing the importance of each source, you may not get better results by itself, so it was not better than all the rules, all the independent model. But then by weight learning, you can actually do better. So you can actually try different combinations, and you can also try automatic weight learning because it's time consuming, I'm not doing it here, and I can get better results. So here is the actual using of this model. I tried for age, gender, and personality prediction of the Facebook users. I couldn't give you the data, unfortunately, so that's why we tried the synthetic data. And this user model is actually used for personalized services, for marketing, for advertisements, so it's a useful model. And here is the results, so it's in a work in progress, but I have a subset of the users. I'm using local predictor, which is logistic regression. I'm also using profile picture of the users and then the Facebook likes. It's about 6,000 users, 49,000 Facebook pages, 725,000 page likes, and this is the result I'm getting. So each source you can see that it has different values for predicting, for example, age, gender, personality traits, and then combining it as a fusion and getting the best results. And you can see, for example, image, the profile picture is a good indicator for the gender of the user, which is not for the age because people are not really updating the profile picture. Okay, so this is the first part of this for the user modeling. I hope you already tried the models and get familiar with the models. Okay. So the second part, we are going to try link prediction. So here,
Quick question.
sure.
So, just thinking about sensor fusion and when you were talking about it,
Yeah.
so if we have different sensors, we have a different confidence for each sensor. Can you just briefly talk about how to incorporate those?
How to incorporate the confidence.
of each sensor?
So the base of the rule is actually that. So you have different confidence based on each source of information. So here we have the source of information, which is differential links, for example. We also have a local predictor, which is the prediction from text and image. These are different sources of information, and each one of them, as we try separately, we see that they have different prediction results. So friendship was not as accurate as the local predictor. Okay. So the base of the rules actually play the role in order to know like which source is better than the other one when we are combining this all together as data fusion framework. Yes.
Just quickly, is the local predictor trained on the exact same input space, or like can you just quickly like what is that running off of? Is that kind of built? You're including it, but you're also comparing it to it.
So
Can you repeat the question?
yes, so the question is how we get this local predictor. So here is assumed that for the users, for some of the users, we have the actual age, gender, personality traits. And then we have the status updates of the user or the profile picture. So based on the training data, we can actually train a model like logistic regression by extracting some features from a text or image and then get the prediction for the test users. So here we want to infer some part of the users that we have their, for example, text and image, we don't know their labels. So we are actually using this logistic regression prediction for those users. That's a local prediction. Yes.
Variation on my previous question, I guess. Let's say we take a look predictor, we make a prediction for everyone, and then for every user we count up from my predictions, how many of these friends of mine are introvert, extrovert. I take that in, and then I run the same model again, and then I just iterate and equal stuff we do. Does that get you something similar to what's coming out of PSL if you know how different it would be doing it that way?
So the thing is that, so the question is that if you are, correct me if I'm wrong, I'm just repeating the question. So if you have this source like this local predictor, you're getting some results, and then you have this friendship links, you can also get some results. So what's the difference of like doing it jointly in PSL, or why PSL is better to do this? Is that the question?
Yeah, is it fundamentally better than doing an initial estimate and then taking counting your estimated relationships, putting them back into a separate model, and running it iteratively, and still listing something again? I guess I'm just trying to understand what's the intuition about what PSL is doing versus what you can do through a manual series of steps.
Okay, so the question is that like if we do it manually, so trying this friendship links and then try this local predictor and then do it iteratively, how it will be different than PSL. The thing about PSL is that we are doing it collectively. So we just run inference once. We try to get the highest probability of all those random variables that we have in the model at the same time using all sorts of information. So it's not iteratively that we are like getting the probability of some random variables and then fix it the next iteration. So we are doing all the random variables at once, so we just run the optimization once. So it is just collectively, jointly inferring all the random variables.
But I guess it's a trade-off in terms of the iterations you're doing to provide that one solution versus iterations you might do for a series of manual steps. Do you know how that pans out?
So iterations for the inference, you mean?
So I guess in the collective estimation that you're doing,
Yeah.
there are a number of iterations to solve this
iteration, so as Eriq already mentioned, the inference in PSL is a complex optimization. So you can solve it in polynomial time. We are doing ADMM, so that's why we do have iterations, because we make it parallel to make it scalable. It's not exactly the same as doing the iteration of like one source and then getting the information from one source and updates the information that we have from another source. We are doing it collectively, so all the random variables that we have in the model, we are getting all the values. But changing the number of iterations actually influence. So what Eriq already did, so one of the parameters that you can try for the inference is the maximum iteration of the ADMM. So by changing that number, you can get better or worse results. We have a default one which actually works better, so it's just try until it gets a fixed point, and not the random variables are changing. Yeah, you can actually like try different iterations.
Okay, thanks.
Okay, yeah.
So if I were to do the weight training, are there any penalization to the weights? Like if I can have a similar idea to regularization, is it possible, or does this concept apply? Let's say I have a lot of rules.
Yes.
And some rules are useful, some rules may not be useful. So do you think the weight training will be, so do you think, if I don't have enough data, so do you think I have some penalization to find out which rules are good, which rules are not good?
That's actually the best idea to do. So if you have some idea like which one of the sources is working better, you can actually initialize the weights and then actually try the weight learning. Because weight learning is learning, so you do need some data to learn it from. Because like we have different type of weight learning, and one of them is the likelihood to the data. So you have to like big enough database in order to do the good weight learning for the sources. So the best idea is actually if you have some intuition which sources works better, you can initialize the weights of the rules and then try weight learning on top of it. Okay.
So are we done in terms of time for are we ready for the next session, or do you have more?
I do have another one, which is the link prediction.
Is it? Okay, let's hope we are. Yeah.
Okay, so I will quickly over there. So here, let's go to the trust prediction. Okay, so we want to try some models here now.
We're a little bit behind. We also have Eriq's entity resolution after that. Is that right?
Yeah.
I will try to go quickly over this. So the one of the other tasks is PSL is very good for is a link prediction. The difference between the link prediction and collective classification is collective classification, we are trying to infer the label of the nodes. Here we are trying to infer the edge. So we are trying to infer the links between the nodes. So one of the things, for example, is like the trust relation between users. This is a running example for this model. So here, so we can actually infer so many different links, like friendship links. Like in Facebook, you are like suggesting some friendship links to you, and that's also link prediction task. Here for the trust prediction is useful for a recommender system to know who is trusting whom in order to suggest some items to them. And the nice thing about PSL is an expressive language. So if you have some theory, you can actually model it in PSL. So this is what we tried here for trust prediction. So this is theory from 1973, which is structural balance theory. What does it mean is that it says that if we have this triangulation between users, we can actually say that if Alice is a friend of Bob and Bob is a friend of Carol, Alice is a friend of Carol. So friends of your friends is your friend. Also, this is another kind of theory that an enemy of your enemy is also your friend. So if Alice is the enemy of Bob and Bob is the enemy of Carol, so Alice is going to trust Carol, so Alice is a friend of Carol. This model is actually published in this paper 2013. So here is some examples of the model, and I want you to read this for me, if one of you can actually read this, because it's very straightforward. So, does anyone want to read this and like tell me? Yes.
trust C is transitive, so A should trust C.
C is yes. Yes. A is trusting C, yes. Yeah. So it's just friends of your friends is your friends. The other one is this enemy of your enemy is your friends. Okay? This is one of the models. So we have the full model. You can actually look at it later. So I'm just going fast forward. The second model is the social status. So it's also from a theory from 1992 in sociology. So it's considering a hierarchy. So it's not exactly the same as the balanced one. So it says that, for example, if you have this triad relationship, if a patient trusting a nurse, nurse is trusting the doctor, but doctor is not going to trust the patient. So it's the opposite of what we've seen. So we can actually try different theories here by modeling it in PSL. So this one is also tried by UAI2018 in 2010 for the trust prediction, actually, this model. So we can actually try it in PSL as well by modeling in this way. You have the full model, so I'm not going through this. You can actually check it later. The third model is actually interesting. So here, we are defining a latent variable. What does it mean is that you want to predict some labels for the nodes here in order to predict this link between them. So what you want to know is whether a person is trusting or trustworthy, right? We don't have any information about it in our data, but we want to infer it based on the links that we already have. So this is a model. So we are saying that if a user A is trusting, so that user is trusting everyone, right? So if user is trusting person, so it's going to trust all the users, like most likely. And if a person is trustworthy, so people are trusting that person, so it seems that people are trusting that person, so we can infer it. If a person is trusting and a person is trustworthy, so it could be the trust relation between these users, okay? The thing about this is that in addition to the link that we want to infer, we also want to infer this trusting and trustworthy for the nodes. That's why it's a latent variable. So we don't have it in the data. It's also open predicates. So let's try the real world data set now. So we have the data from the opinion network. It's about 8.7 thousand trust links. And if you go to this directory, which is trust prediction, we want to try this balanced status and latency model now. So I want you to open the PSL model. If you go to this directory, so if you go to CLI, what you have here, this trust prediction of PSL, is actually a balance model. So if you open it, so this is the balance model. So we have actually 16 different transitivity relations. And we also have priors to say that if two people know each other, they may trust each other and stuff. And because these triad relations, if we are not bounding it, we have many pairs of relations, we are bounding it with nodes. So what does it mean is that we are predicting the trust relation between two users, if and only if they know each other. If they are not knowing each other, we cannot infer they may trust each other or not. So if you run the model, you will get the results for the balance model, which is the first model. We also, I want to also look at the data file for this. So we have the nodes relation, which is closed. But what we are inferring here is a trust. So the trust relation is open. So our target is trust, okay? It's also the same for social status. So the data file would be the same. If you want to try the social status model, you have to go to this alternative models directory and get the trust prediction status one, copy paste it to the CLI and make the trust prediction PSL model, and then you can run it again, and then you will get it. I will show you the results. It will take some time, so you can also try it and you will get the results as well. The third model is the latent model. So here you can see that we have less number of rules, that we have the model with trust relationship between users based on these latent variables, trusting and trustworthy. So you can also get this model from the alternative model folder, which is the trust prediction and latent. So I can actually show you now this. So here we get the results for the first model. So we have a area under the curve of 0.80, and we have a positive and a negative class. And in the trust prediction, the importance is the negative, because we don't have that much of information about the people who are not trusting each other. So it's really important to predict the distrust relation, because we can actually predict that everyone is trusting each other. Okay, so I want to just show you the alternative models. So, okay, here you have the balanced one, you have the latent model, and you have the status model. So if you want to create a latent model, you have to copy this one to the CLI for one. For the latent model, we also need to change the data file. Why? Because we have two other predicates which are open, and it's different than the status and the balanced one. So let me show you the data file for the latent model. So that if you look at it, okay. So in addition to the trust relation which was open, we have two additional one, which is trusting and trustworthy. Okay. The difference here is that, as Eriq already mentioned in the first session, is that you cannot try the map inference if you have more than one open predicate here. So what you should do is you have to try the lazy inference. What does lazy inference do is, oops, okay. So the map inference, you already seen this. So we have the rules, data, we are grounding, and then we get the potential function, and then we have the random variables that we want to try the inference on. For the lazy inference, we have to do it iteratively. So first, we are trying to infer the random variables as we can, and then the next iteration, we see if there's any random variables that we can actually infer based on what we already have, and then we do the iteration. So we are doing the lazy inference. That's what they call lazy inference, because it's try like what it's seen. And then it's iteratively doing it until there's no additional random variables that the values is changing or it's a new random variable. So for the latent model, we have to try the lazy map inference. So how you can try it, you actually need to go to the run.sh. So that's what we're going to do now. So what you should do is actually we have to copy this trust latent PSL model to the CLI one. Oh, it's not CLI, but okay, that's right. And then the latent data one. Yeah. And then because what is this? Okay, so now we have this. So we have to change the name of this to, so I will remove the trust model that we had before, which is a balanced one, and then also the data file for it. And then change the name of this file to the model that we want to try. Also, I will do the same for the data file. So you should also do the same with me. I just wanted to try this model with you to know how you can actually run it. Okay. So this is how we are making the data. So if you go to the run, here, if you don't have any parameters here set for inference, it's going to be map inference. But if you want to try the lazy inference, you have to change the parameter here. So I actually mentioned it here, that what is the parameter that you have to try. So let's, okay, I have to do something about this. Okay, let's copy this, and then we will save this, and then we will run it again.
Wait, Golnoosh, you gotta
Yes.
rename your trust prediction.data. It should be trust prediction eval.data.
Oh, I see. Okay, sorry. Thanks. So yeah.
Change the source.
Oh, okay. Sorry. Yeah, it should be.
Yep.
This one. Okay. Thank you. So now you can run this model, and because you're doing the lazy inference, you can see that. Okay. So this is the results of the latent model, which is 91, which is better than the balanced model you've already seen. One thing about this is that all the prediction results is going to a folder here, which is the inferred predicates. Okay, so if you go to this folder, you can actually see that during the inference, you're inferring all the open predicates. So you're also inferring who is trusting whom, also like who is trustworthy and who is trusting. We don't have any data for it, but we are inferring it, so we can actually look at it to get some idea about this. So let's go back. So if you try these models, you can get these results, and I'm encouraging you to actually try it. And you can see that this latent model is actually performing very well, both on the negative trust relations, or distrust relations, and also the positive one. So this one is actually, so I'm just encouraging you to try base learning and try other combinations, because I'm not combining the models here, so I'm just leaving it to you that combine different models to see whether you can actually improve this model. You can actually try different rules and come up with these different trust relations. These models actually used in this paper, and they compared with the state-of-the-art models at that time, and they show that actually latent model works very well. So here we just tried on one of the folds, but you have the data set, so you can actually try this 8-fold cross-validation and see the results. So that's it. If there's any questions.
Thank you, Golnoosh, and we'll have time to ask questions later. We're a little bit behind
Oh,
time. Let's